Welcome back to Epstem. On this episode, we're going to be talking about a paper related to ceramics. And the paper's title is A General Method to Synthesize and Sinter Bulk Ceramics in Seconds. The paper today goes into a different processing method of ceramics to make them more efficiently and to change different attributes about the ceramics. Ceramics play a big role in your life because with material sciences, ceramics, metals, and polymers are the three main groups of materials in general. And ceramics being able to be manufactured quicker and to change the attributes could make tremendous leaps in many different directions in many different fields. I'm Luke. And I'm Hunter. And you're listening to Epistem, a show where we explore papers in STEM fields and let you know what they're all about.
First, I want to give you some background on ceramics and how advanced ceramics are designed, where they come from, and then kind of get into the research itself, which is about what we're able to do to speed up this process of discovering new materials. So let's start with ceramics. What's up with them? What's up with ceramics? All right, so ceramics are pretty cool and very common, and they've also been around for a very long time. Unlike plastics, which have been around, has it been 100 years? Has it even been that? I don't know when they came around.
Honestly, I would doubt that they're more than 100 years old.
Yeah, so ceramics, on the other hand, are very old technology. Something I found online, one article I found dated them back to 26,000 years ago, at which they were in the form of bricks or porcelain vases. If you've ever been to a museum of history or something like that, maybe you've seen those really old, like ancient Egyptian vases or anything like that. Porcelain is a type of ceramic. Bricks are also a form of ceramics, like mud bricks. So very old technology and can be found in virtually every ancient and modern society. Pretty much any kind of clay or powdery substance that you can bake into a hard material is a ceramic. So that includes glass, plates, pottery. The reason ceramics are a big deal today goes beyond their application as plates and coffee mugs, although those are important as well. Ceramics from a material science perspective are attractive because of a few reasons. One would be that they're very heat resistant, so they don't shrink or grow at all when they get hot, or a very insignificant amount anyways. They can handle very extreme temperatures, which makes them attractive for use in spark plugs in a gasoline engine. Pretty much every gasoline engine car out there has got ceramic spark plugs in it. Also as tiles on the outsides of spacecraft and in crock pots, which isn't quite as extreme, but it's important. So they're all over the place for their temperature resistance. They're also great electrical insulators, so electric fields have a hard time passing through them, which is important in applications where you need to maintain a dependable, pure, high-quality electrical signal. So as a signal integrity application.
In the electronic field, capacitors actually use ceramics also for an insulator.
Yeah, I've seen that. Ceramic capacitors are little red ones, right?
Mm-hmm. Or red or yellow, usually.
Kind of mud-colored.
Mm-hmm.
Like a brick.
Like a brick.
Yes. Yet another attractive quality is their hardness. So they're sharp and they're resistant to scratches. This property is related to their very rigid structure, which is unfortunately part of where their downsides start to show up, because with them being so rigid, they're really resistant to bending or deforming, and because of this, they will shatter or crack instead of bending, which sometimes is not what you want. But those properties do have a lot of positive applications. All right, so that's ceramics basically. The way that new ceramic materials are discovered oftentimes involves a lot of trial and error. Scientists use what they know about certain elements and compounds to mix them in new ways to produce potentially useful new materials, but they can't really be sure that it's going to work until they test it, because sometimes things that work in theory don't work so well in practice. And part of the thing that makes it difficult to test the new ceramics is how long it takes to process them. So you've got to bake the materials that go into the ceramic. You've got to bake them over a long time. It can take hours to cure the ceramic. So naturally, there are going to be a lot of possible combinations of ingredients that could be processed into a new ceramic material, and that's probably more than we could ever realistically test on our own. Some new combinations of the essential bits are useless, and some are identical or functionally identical to others that already exist. So there's a lot of potential for redundancy as well, and this becomes a big challenge for material discovery, but that's where machine learning comes in. Now, machine learning is pretty complicated, but all you really need to know about it is that, in essence, you just give a computer a ton of information about something, and you let it process the information in some way. Now, whether you're aware of what it's doing with the information or not doesn't really matter. But you keep feeding it information and let it keep trying to process the information that you're giving it until it starts doing a good job with it. And then, just like that, you've got a computer which can sort or process or classify data, whatever it is you're using this algorithm for. But essentially what's happening here in this application is the computer is doing the job of the scientist. So the material scientist will show a computer a bunch of compounds and elements and teach to the computer how they fit together. So the material scientist gives the computer some rules for what to do with these elements and compounds. They can also teach it how to interpret charts or graphs or how to compare different qualities or numbers and use all kinds of equations and things like that. And what the computer then does is it applies this process to several other combinations of compounds, and it can predict how they might behave. It's the same thing material scientists have been doing, but it's much faster and potentially more thorough. So it doesn't require somebody to be sitting down doing a lot of math, doing a lot of testing over and over and over again. It does this process just much faster.
If you're a day one fan of EPSTEM, you can actually relate this to the first episode, The Immortal Machine. They use similar microcontrollers and similar systems that are closed loop to actually get that feedback and be able to evolve itself and be able to get the sensor values that they're looking for.
Right, the system adapts over time based on input.
Exactly.
Yeah. So if you start using this, now you have a bunch of potentially useful recipes for new ceramic materials, and all you have to do is test them to verify that they actually work as intended. This is where it gets kind of tricky from a manufacturing sense, because traditionally, like I said earlier, forming ceramics can take hours. And what's the point of having a computer that can spit out all these new recipes super fast if it still takes you hours or days to test a single one? So you're missing the other half of this speedy material discovery. And this is where the research team comes in. So what they've done is found a way to test these materials really quickly. In a nutshell, the researchers figured out how to take experimental samples, which are called precursors. It's basically just the ingredients that once processed will turn into a ceramic material. And they turn them into ceramics in a matter of seconds. This is a very big difference compared to the hours or days. This changes the game because now, not only can you generate new ceramic recipes super fast, but you can also test them quickly as well.
Well, if you found this part of the episode interesting, get ready to learn a little bit more about why ceramic processing works and why it needs to be more efficient. We'll see you back after this ad. Well, welcome back to the show, and Luke will now tell you more about ceramics and how they work.
So how does this process work? How is this possible to produce ceramics so quickly compared to how they've always been processed? It really comes down to this, what's known as ultra-fast high-temperature sintering, or UHS for short. Let's break it down a little bit to talk about what that means. So the ultra-fast portion is pretty obvious. They call it that because the whole process from heating to processing to cooling takes place in less than a minute. And just a reminder, a conventional process takes several hours to do the same thing. The high temperature sintering portion is just describing the process taking place. Sintering is simply the process of turning a powder into a solid using heat and or pressure. It's actually a pretty simple process that works in a similar manner to a toaster. In a toaster, you sandwich a slice of bread or an English muffin or a bagel or Pop-Tart or whatever you put in toasters. I'm not going to judge you.
Pizza.
You put that in between a bunch of metal strips that get super hot and glow red when electricity flows through them. This heat is transferred directly to the bread, and then you've got your toast. So in this case, replace the bread with a little precursor pre-ceramic powder and replace the heating strips with carbon paper. This carbon ceramic sandwich is really all there is to the UHS process. The magic behind it all is really just in how quickly the carbon strips can reach the ultra high temperatures necessary and transfer them to the precursor to create that sample. one of the benefits is that you can squeeze a lot of these precursors into the carbon strips at once, so you can process multiple at a time. You can even do different materials at a time, so you can process and test multiple different, I'll call them recipes, potentially useful new materials all at the same time. This type of heating is formally known as resistive heating or joule heating, and it's really interesting when you do it with carbon strips or carbon nanotubes. But that's beyond the scope of this paper, so you'll have to tune into the curiosities if you want to learn more about that. So with that, I think it's time to get into the nerd notes just for a couple quick points. I've only got 2 points I want to talk about. And first I want to talk about one of the interesting ways that you can prepare a precursor. So just a reminder, the precursor is that, if you want to think of it as the raw ingredients that you put into the joule strips that you heat, that eventually turns into a ceramic. So one of the interesting ways you can do this is by using what's called a polymer derived ceramic. So basically what this is, it's a special plastic that when it experiences extreme heats, it decomposes into a ceramic. Now because it's plastic, you can process it with a variety of methods, such as stereolithography, or a process that can give you otherwise unique geometry. If you've never seen 3D printed parts, you can get some pretty crazy shapes with them that you wouldn't be able to achieve with conventional reductive manufacturing techniques like milling or drilling or anything like that.
With current technologies, this research is even more immense because, as Luke said, stereolithography, with that, actually there's a lot of computer generation and a lot of computer simulated designs nowadays that can be generated to optimize stress points, optimize different variables about a structure of a system, and then create an STL, a stereolithic file from that. So with these two technologies combined together, it could create a lot of different ways that ceramics can be used where they haven't been able to be used in the past.
Yeah, it kind of takes the pros of processing a plastic with the pros of the positive qualities and properties of ceramic materials, and it kind of puts them together. Mm-hmm. So yeah, you can just, anything you can make, well, I don't want to say anything because there probably are some limitations using this special plastic, but we won't get into those. But in a nutshell, anything that you can make with a 3D printer, as long as you use a special plastic, you can heat it this way, process it this way, and you can turn it into a ceramic. It's pretty crazy to think that you can turn a plastic into glass pretty much, or something that has a similar properties as glass. So you can get really complicated geometry. Another interesting thing is the properties that you can tune a ceramic for. So in the paper they mentioned that you can tune these ceramic discs for piezoresistivity response. So basically this could be used in any kind of application where you'd want a sensor to be aware of mechanical signals traveling through a device or an object. So acoustic guitars actually use piezo resistance pickups to pick up the sounds of the mechanical waves coming in from the strings of the guitar, and that's what's sent to an amplifier. So really any kind of mechanical signal that travels through something could be picked up by a piezo resistance, and you can tune your ceramics for a response to that. You can also tune your ceramic to be responsive to magnetic changes and changes in magnetic flux around the ceramic. So those are some applications that you can tune for. You can really optimize the material for that, and there's probably some ridiculous number of applications just within electronics or technology for those.
Well, that's all we have for the episode today. We have a lot planned for the Curiosities next week, where we're going to dive more into ceramics and the manufacturing of them to bring that to you guys at a more lax manner. To reiterate, this paper is titled A General Method to Synthesize and Sinter Bulk Ceramics in Seconds, and the researchers that did this are Shengwei Wang, Weiwei Ping, Xiang Bei, Huachen Ku, Ryan Hensley, Ruyu Wang, Alexandra Brozena, Zhenpeng Zhu, Jacques Day, Yang Pei, Xiaolong Zhang, Glenn Pastel, Zhilong Gao, Zhizheng Wang, Howard Wang, Zhisheng Zhao, Bao Yang, Rain Zhang, Jian Liu, Yifei Mo, Bruce Dunn, Lingbing Hu. This can be found in the 368th Science Journal publication. Thank you again for listening. If you really enjoyed the show, please follow us on Instagram at epi.stem.
Or you could reach out to us with questions, concerns, feedback, ideas, proposals, suggestions. Did I say suggestions already?
Not yet.
Well, there we go. Suggestions. I'll say it again.
Decrees.
And our email is epistem.pod@gmail.com.
And if you're feeling really generous, hit us up on Patreon. www.patreon.com/epistem. Bow down now.
Down, down, down. Down, down, down. Down, down, down. I want to talk about me.